Okay, welcome again to our journey into number theory, and we mentioned last time that we're going to move on to looking at this thing called the Dirichlet divisor problem. And we had a little lemma that told us that we could get a rough estimate of this sum, n less or equal to x1 on n, and it's log x plus gamma, which is Euler's constant, plus big O 1 over x. And I then stated, we haven't done the proof of it yet, I've stated this result which goes back to Dirichlet 1838, which tells us that the sum n less or equal to x of tor of n, this is the number of divisors of n, turns out to be x log x plus 2 gamma minus 1 times x, where gamma's the Euler constant, plus big O root x. And as I mentioned, then if we divide everything by x and average out, then we get the average value of tor of n is log x plus a constant plus big O 1 on root x. In other words, it's roughly log x. And as I showed you in the diagram there, that we can take the values of tor of n, which look like this, that are all over the place, and if we average them out and we draw the picture here, we get a graph like this. And although it's not exact, of course, it's got lots of wobbles in it, but it's roughly looking like a logarithm function, which is quite dramatic, that you're going from something where the data's all over the place to something which looks reasonably consistent. Now we're going to do a little proof of this, and the proof is quite pretty. This is the one that goes back essentially to Dirichlet. So this number tor of n, which is counting the number of factors of n, another way of thinking of it is to count the number of lattice points of the form x, y, lattice points meaning x and y have to be integers, lying on the parabola xy is n in the first quadrant. And hence this sum, n less or equal to capital N, is simply the number of lattice points with positive coordinates lying under and on, if n is an integer, the hyperbola xy equals n. And so that invites us to draw some pictures and to look at the problem graphically. So here's our hyperbola xy equals n, and so in the diagram the number of I'm going to look at this particular little square in here, so I'm going to go across to root n and up to root n. So in the picture, the number of lattice points lying inside this square is obviously, it's just the floor of the square root of n squared, so that's the base times the height. And by symmetry, the number of lattice points that lie in this region A1 is equal to the number of lattice points in A2, and so we can just concentrate on, say, A1. So we're going to take a line at x equals r here, somewhere between 1 and root n, and the number of lattice points then in A1 is simply going to be n over r minus root n. So the number of lattice points lying on this particular line in A1, I should say, is equal to that, because you'll get n over r is the y value at this point, take the floor, and the square root of n is the y value at this point. So if we subtract those, that'll give me the number of lattice points on each one of these lines. So the total number of lattice points, so on it, that's what we have on any particular line, so the total number then is just going to be the sum where r goes from 1, the sum r goes from 1 up to the floor of root n of this expression here, and then we double it because the number of lattice points in A2 is the same, plus the number of lattice points in the square in the middle. So that gets us that formula. Now we can estimate the floor of y we can write as y plus a little bit, which is just going to be a number bounded by 1, so I can write that as big O of 1. And I can then use that little identity in here and here, and I can replace this then with, I've changed the sum from R to N, by the way, here. So I've just changed the dummy variable here. So this is now N over N plus big O1 minus, now I'm adding this one up. This is R independent, so this is just going to be that number multiplied by that. And there was a 2 out the front, so this is minus twice the square root, floor of the square root of n squared, plus that one we copy down. These two we can combine together to this. And if I take a function which is big O1 and I add it up from n equals 1 to the floor of root n, then I just have a function which is big O root n. So that's where that's coming from. And I've taken the n out the front, so I get 2n times this sum. These two terms combine to give me this one, and then the big O1 turns into a big O root n when I sum it from n equals 1 to root n. Finally then, what do I do now? Well, I say that this, again, I can replace this with an n, and there'll be a little bit extra, and I bury that in the big O root n. So I said before, this big O is very useful for sweeping things under the carpet, so this won't be exactly equal to that if n is not a square, but the difference will be something which is small, and I can shove it in the big O root n. Finally then, I can then say that, so replacing this with x, so the sum n less or equal to x tor of n then is 2x n equals 1 up to floor of root x 1 on n minus x plus big O root x. I'm just replacing all the n's with x's. And now from our lemma, we know how to sum this thing from the lemma, so I can simply replace this now. This is the sum up to the square root of x, so this is now log of this number, that's log of root x, plus gamma plus big O1 on root x, and then minus x plus big O root x. And finally, when we simplify this using the log laws, we're going to get x log x. I'm going to get x into 2 gamma minus 1, and then I can combine these together if it's big O1 on root x and big O root x is big O root x. And that's the desired result. And so once again, if we take the average then and divide this by x, we see that the average is roughly log x. So that is a very nice result. That goes back, as I said, to Dirichlet. Now, the so-called error term here is this big O root x here, and we've done a fair bit of hand waving and shoving things under carpets to get to here, and the question is, can you improve this thing? Can you get it to be smaller? This is at the moment x to the half. So let me just say a word about that. The error term, a big O root x, has been improved. The determination of the best possible error bound is known as the Dirichlet divisor problem. Now, the most recent results of which I'm aware are that I can replace that root x, that x to the half, can be replaced by x to the 7 on 22. That was done in 1988. And in 1990, it was improved again by Van der Loon and Wattle to x to the quarter log x. And more recently, in 2003, Huxley reduced the power of x to this number. Hardy and Landau showed right back in 1915 that 1/4 was a lower bound for this fraction. So it's hoped that you could replace the x to the half by x to the quarter, and it's widely believed that that's the true order. but no proof of this has ever been found. It remains an open problem. And as I said, the most recent result is this one, back in 2003. Now, in order to get the order of sigma, the sum of the divisors, so once again we'd like to know what's happening with sigma, we need again a couple of little results, which I put in a lemma here. The first one says that if we've seen how to get a formula for the sum of 1 over n. Now I'm going to look at 1 over n to the s for s bigger than 1, and I can get an estimate of the size of this. It turns out to be x to the 1 minus s on 1 minus s plus zeta of s, here's the zeta function coming in again, plus big O x to the minus s. And the order of the tail of the infinite series, if I look now at n bigger than x, 1 over n to the s, this turns out to be of order big O x to the 1 minus s, if s is bigger than 1. And we're going to need these two when we get to examining the true order of s. So a little proof of this result, of this lemma. And so there it is. They're the things we're trying to prove. We want this. We want the order of. We want to try and get an idea of the growth rate of this sum n less or equal to x 1 over n to the s for s bigger than 1. And then we want to get some estimate of the tail of the infinite series. So for both parts, I'm going to assume that s is bigger than 1 and x is bigger than 1. And now I can use that lovely theorem we had before that tells us how to work out these sums. We simply take an integral of 1 over, replace n with t, so 1 over t to the s, and we're going to integrate from 1 to x. Plus there's going to be some constant that depends on s, plus big O 1 over x to the s. Now this is an easy integral, so I can integrate this, put in the endpoints and subtract, and I just get x to the 1 minus s on 1 minus s minus 1 over 1 minus s. Copy this down. And this is a function of s, well so is this. This is a simple function only of s here, so I'm going to combine these two together and call it k1 of s. Copy the rest down. And now I'm going to see what happens as x goes to infinity. So as x goes to infinity, remember s is bigger than 1, so this goes to 0. This, whatever function is hiding in here, this is going to 0. And so I'm simply left with this sum here as x goes to infinity. Well, this is my zeta function as s goes to infinity, and that means my k1 was just equal to zeta of s. And if we plug that all back in, we get the desired result. For part B, well, we're looking at the tail now, and so that's going to be now the tail of zeta of s. So this is zeta of s minus the terms for n less or equal to x, 1 on n to the s. And we've worked out what this sum was, so looking at what we had above, zeta minus this simply gives me x to the 1 minus s on s minus 1 plus big O 1 over x to the s. And because x to the minus s is less than x to the 1 minus s for s bigger than 1, then I can simply say that any function, this one is going to be less than this one, and so I can write the whole thing as big O x to the 1 minus s. Now, by the way, just observe here that in the case when s is 2, then this gives me this nice fact that the sum of the reciprocals of the squares for n less or equal to x, so it's a finite sum, is minus 1 over x. This is just putting s equals 2 into the formula above, plus zeta of 2, which is pi squared on 6, plus big O 1 on x squared. And we'll use that little result in the analysis of working out the average value of sigma. So that's a little proof of our lemma. That's the lemma that we had here. We've now established both of these results. And finally, to proceed with sigma and also with later on with phi, and in fact to examine lots of other averages, we need these identities which I call the Dirichlet Sum Identities. And there are two of these. I'm going to call this DS1 and DS2. This is the Dirichlet Sum Identity number 1, Dirichlet Sum Identity number 2. These are just technical expressions, technical identities I should say, which enable us to simplify sums. So first one says if g is an arithmetic function, then you take n less or equal, so you fix x, you take the sum of all the integers less or equal to x, and once you've got your n, you then take all the divisors of n, and you sum g of d over the divisors of n, where n's less or equal to x. Probably best to read it backwards. So we want the sum of g, sum over the divisors of n, and then the sum of all that is n less or equal to x. And we can write that as the sum n less or equal to x, sum of d is less or equal to x over n, time sum g of d. And that one's called the Dirichlet divisor identity 1. And the second one's got two arithmetic functions f and g. And again, this one here, we take the sum of f of n for n less or equal to x times the sum of g over all the divisors of n. And that turns out to equal the sum of g of d, d less or equal to x, times the sum of f of dj, these are all the multiples of d, for j less than x over d. Now these look complicated, and they are. They're not easy to get your head around, but they're very, very useful. You'll see when we actually apply these and put some actual functions in here, these turn out to be extremely useful identities. So DS1, DS2. So I'm going to, just to give a quick proof of these, I'm actually going to do the more complicated one first, a complicated looking one first, because it actually turns out to be in some ways slightly easier than the first one, and we can get the first one from the second. So I do part B first and then use it to do part A. There are other ways of doing it. You might like to come up with your own proofs of part A independent of B. Anyway, for part B, this is the sum on the left-hand side. So it's the sum of all of f of n's, n less or equal to x. And then for each of these n's, we sum g of d over the divisors of n. Now what I'm going to do is I'm going to write this thing out to show you what it looks like. So I take n to be 1, so I put f of 1. And now I take the divisors, so I now have n is 1. I put n as 1 in here. The only divisor of 1 is 1, so this becomes f1 g1. That's the first term. Now I put n to be 2 in, so I get f of 2 times the sum over the divisors of 2. Well, that's 1 and 2, and that's the next term. Then I put n as 3 in, so I get f3, and the only divisors of 3 are 1 and 3. And then I put n as 4. Divisors of 4 are 1, 2, and 4. And then you just keep going. Now I'm going to rearrange, these are finite series, so I can rearrange the order of these terms without any problem. And notice that I've got a g of 1, and that's going to be f1 plus f2 plus f3 plus f4 and so on. Plus g2. Now where's the g2? The g2 is here times f of 2. The g2 is here times f of 4. And you see you're going to get all the multiples of 2 there. And then I take g of 3, and it's g of 3 times f3. If you write some more terms, you'll see the next one is f6, and so on, and see these are the multiples of 3. And now all I now do is simply write this back in sigma notation, So we now take d less or equal to x of g of d. So that is d is 1, 2 and 3 and so on. And then I multiply it by this sum, which is simply the multiples of d less or equal to x. And so in the case when d is 1, the multiples of 1 are 1, 2, 3 and so on. If d is 2, the multiples of 2 are 2, 4, 6. Multiples of 3 are 3, 6, 9 and so on. And so we see this is exactly the sum we had here, and that was the right-hand side of our identity. Now we can get part A now. Either you can do it bare hands without using this, or all I'm going to do here is I'm going to put f to be 1 in the above result, which gives me that, which gives me this. Sorry, I should say which gives me this here on the left-hand side equals putting f as 1 equals to that on the right-hand side. Now the right-hand side of what we had to prove was this quantity, and I can write this as the sum over n and d, where nd is less or equal to x of g of d. And what I'm doing here is I'm going to change the roles of n and d around the other way, so I'm going to sum for d less or equal to x, and then n is less than x over d, just rearranging this, of 1, and I just relabel the n as j so that it fits with the identity I wrote down for part A. And so that's the proof of these divisor to sum identities. Now I'm going to state the next result, and we'll do the proof in the following video, but we can now write down a theorem which tells us the average rate, which tells us the sum, the partial sums of sigma of n for n less or equal to x. And it turns out to be pi squared x squared on 12 plus big O x log x. Now immediately one should be a little bit taken aback here that pi suddenly appears in this approximation. That the sum of the sum over the sum of the divisors is roughly pi squared x squared on 12 plus this error term. Which, by the way, means then if I take an average, if I divide this by x, that says the average of the partial averages of the sigma function is equal to pi squared x on 12. That is, it's pi squared on 12 times x, which is linear, plus big O log x. Now we can see this happening graphically, and I always think this is quite dramatic, really. This is rather beautiful, remarkable result. So there's my sigma of n. Again, it's all over the place. If you've got primes, then sigma of a prime is just 1 plus p, so that'll be small. And if you've got numbers that have got lots of factors, then when you add them up, you'll get large values of sigma. So again, it's all over the shop. It's hard to know what's going on here. However, if you take the average, and here's a graph of the average now, and you should be, I hope, appropriately amazed that the average is looking roughly linear. It's not exactly, of course, it wobbles around, but it's roughly linear. And of course one then asks, if it's roughly linear, what's the rough gradient of this line? Well, just as these numbers are very small, of course, but I've just noted here if we go up to 60, it's roughly 50 on here. And 50 on 60, trying to measure the gradient, is about 0.833. And pi squared on 12 is 0.822. Now again, we're only doing it for small numbers here, but you can see what's going on here. That the average of sigma is approximately a straight line, and the gradient of the straight line is approximately pi squared on 12. And we'll see how to prove that in the next video.